with a presentation titled Increasing Automotive Safety and Reliability with Component Authentication is Michael Haight, Director of the Micro, Security and Software Business Unit at Maxim Integrated Products. Michael, over to you.
Thank you, Nick. It's no surprise to most of us that automotive electronic content is prolific and expanding, and content that was seen in previous years just on premium vehicles has now broadened its reach. It's gone downstream to middle tier and even entry point automobiles. And that's become expected by consumers, and especially as the electrification of vehicles and transition away from combustion engines is underway and only accelerating. That's leading to new architectures that will have more electronic content, as well as the driver assist features and increasing levels of ADAS. Now, with the increase on electronic content, there are more security attack surfaces that the bad players of the world can exploit. And so the security risks are going to increase as well. I would say the most infamous attack for automotive that has happened in the past was about 2 years ago. Two researchers attempted to apprehend and were successful apprehending an SUV. And as a result of that, the car manufacturer recalled 1.4 million cars. And in their annual report, they said that there was a Jeep voluntary recall cost that was 115 million euros, which is about 135 million US dollars. So that's quite a bit of money, but in relative terms, it could be much worse. Some studies show that that could be up in the $1 billion range. And so extremely large amounts of money, a lot of risks here. Many in the electronics industry and even in just consumer space are hearing more and more about familiar cybersecurity attacks. A few years back, we had a crypto worm that was going through called WannaCry, and if you didn't pay the attackers a certain amount of money, it would lock up your machine. It's a distributed denial of service attack. We also heard cases of Wi-Fi connected baby monitors that could be infiltrated from people in different countries or even continents, snooping on loved ones. It's a very creepy situation. We also are constantly hearing about theft of identity with different IDs, credit cards, and so forth. So it stands to reason that with more content on automobiles, that we could see similar categories of attacks. So with a whole system or a fleet of autonomous cars, for example, a denial of service attack could just shut down a whole city and all of the cars just stop, and nobody could continue to drive around in the cars at that point. With more and more cameras appearing in cars, driver monitoring systems face the driver side, but also many cars are adding cabin occupancy cameras. And so we could have people snooping in on those cars as well, another creepy situation. And then with autonomous cars, perhaps somebody sitting in a different continent could steal a vehicle and have the car just drive off. So a lot of different security vulnerabilities are coming into play. There's a standard called ISO 21434 it's still in the development phase, but one of the things it spells out is cybersecurity lifecycle. And so going through the different phases of life, from all the way from concept and design through the production, operation, even a backward maintenance path, and then finally through decommission. Security must be considered through all of these aspects. So that's good that that's being taken into account by standards bodies. But in addition to some of these vulnerabilities that we've described, some pieces that may not be getting as much attention are counterfeits and theft and supply chain. So some studies show that between 20 and 45 billion US dollars are the estimated annual market size for counterfeit components. Large numbers are seized every year. And then with theft, certainly large dollar amounts of vehicles are stolen every year. And one study showed that people took one of the most commonly stolen vehicles, a Toyota Camry, took the 15 most commonly replaced components off of it, and then they were able to sell that on the open market for $11,000 US. So that prevents kind of a perverse incentive for the nefarious people in the world to continue to steal parts and steal cars. Supply chains are another area that almost a third of automotive suppliers don't even have an established security team, cybersecurity team, according to one study. Another study shows that almost 2/3 of the organizations just aren't testing for different attack surfaces and vulnerabilities their parts might have. An industry expert, Ken Monroe, suggested that he thinks the problem is not so much in the OEMs. The car makers may have cybersecurity teams, but just with the increasing web of suppliers in the market, that's where the vulnerabilities might lie. So it goes to stand that genuine parts are the safest and most reliable, especially as more and more mission-critical functions are implemented in electronics. And so they could be actually dangerous for some of the mission-critical components if they're not performing to specification. And it would be annoying at worst. You might get warning messages or functions may not work. But to give a little more detail on some of the dangers for counterfeit components, for example, with the driver assist features or ADAS sensors, you have this network or ecosystem of sensors that are collecting information from the environment, feeding it into a processor, and the car is making decisions on what to do. And so poorly performing aftermarket or counterfeit components might be dangerous. Airbags, we've seen some studies where an airbag was replaced during a routine service visit, and the driver didn't even know that the garage replaced it with the counterfeit. It didn't deploy, and the driver lost their life. Very unfortunate, tragic situation. We also know that lithium-ion batteries have some danger for catching on fire. We've seen reports in aircraft, smartphones, and many other components. So if you have a whole fleet of cars using this lithium-ion technology, for batteries that are not using the highest quality construction techniques, there may be some vulnerability of fires. There are a number of components that are vulnerable to theft. And so some examples, front light modules. They're becoming increasingly sophisticated with digital matrices in some cases of LEDs and the electronics to power those LEDs. They're an external component, and so thieves can remove them. It's very costly to replace. Premium level vehicles may have some quite costly alloy wheels, sometimes up in the $1,000 to $2,000 along with their tire pressure monitoring system. And then we've heard for years and years of thieves just simply smashing a window and stealing the infotainment right out of the car. Now, it's kind of common sense to most everybody that different levels of what you're trying to protect require different levels of security. And so if we split this up into 3 tiers of full, medium, and light, on the full side, we see a safe here, and there's a network of laser beams that somebody would have to dodge through these lasers. Then they would have to get to the safe and figure out what the combination is. One can imagine that there's something extremely valuable in that safe. Likewise, many of us have traveled to hotels where there are safes in the room. You can store passports, phones, keys, similar things to that are maybe a medium value, but this is not too cumbersome to store it in there to punch in your PIN code. And then finally, on the light side, the good old-fashioned padlock is very effective at protecting a number of things. It's very easy to snap that lock on. Now, another concept that I want to introduce in addition to these splitting security up into 3 levels would be a differentiation between encryption and authentication. Many people just assume automatically that if you put security on, that means you're encrypting data. You've got a bunch of garbled characters that you really can't make sense of unless you know a secret. But that's not always the case. And in a number of cases, you may want to just protect data and know that the source of that data is genuine, it's legitimate. You don't really care if the data is protected or garbled up. You could read it, but you want to see a signature and know that signature came from the same source that provided the data. Now, what are some solutions that can address some of these different areas from the high, middle to low? If we follow these same categories or same partitions, at the highest level, a hardware security module or an HSM is a very high performance microcontroller, provides a great deal of flexibility, full toolbox of algorithms. You can manage numerous keys and provide encryption. And then in the middle tier, you'd have what we call a trusted platform module or TPM. And generally, you may have a fixed function. You don't have as much flexibility as a microcontroller, but it offers a pretty good set of algorithms. There's not as much need to develop code. And then it often enables transport layer security. That's the same protocol that's used for most internet transactions today. And so encrypting a channel between the 2 points following this approach. And then finally, the secure authenticator is really targeted. And so if you really narrow down to a specific algorithm or maybe a small number of algorithms, you can reduce the area, the size of the solution. You can make it more simple, and then the implementation is much easier. You don't necessarily need to encrypt the data. Sometimes you just want to authenticate it. Now, looking at these three categories, they fit very nicely if you look at a range of performance metrics such as power consumption, board area, pin count, cost, and development ease and resources required. And from there, you may see that there are certain parts of a car that in the past, if HSMs and TPMs were all that were available, you just wouldn't add security to begin with. You might, the OEMs might determine that the risk of compromise is lower than the cost of adding security. And so by having authenticators as the light side, it opens up a new market of protecting components that just may not have been protected in the past. So to talk a little bit more about an authenticator, how is it typically used? Most cars have a number of electronic control units, and those are talking to different endpoints. Some ECUs already have an HSM or a TPM in them for other functions. And so if that's the case, then by just adding one component on the endpoint, an authenticator, the HSM can do all of the transactions. It can be paired up with these endpoints, and it can then authenticate every time you start up the car, for example, go out and pull all of these endpoints to make sure that they're authentic. And then if firmware updates need to happen, authenticators can even verify signatures are correct, and so you're getting the right firmware. It's not compromised with any kind of malware. And data coming off of the endpoints can be authenticated or signed by a secure authenticator. And so how can you raise the security bar with just one chip? Well, it's like we were just describing. If there's already an HSM or in the ECU side, you just add one chip to add security to the module. If you use that same approach for a number of modules, then the endpoints can all share a common security platform, and key management can be very easy. So to name an algorithm, the elliptic curve digital signature algorithm, or ECDSA, is one that uses a public key and a private key. And so a private key can be embedded in the authenticator. That public key associated with it can be distributed freely outside of it to the ECU side or anywhere else for that matter. So key management is made very easy. And authenticators can help meet the ISO 21434 security goals to ensure that all product life phases are covered by security. And then with these approaches, you can have a bidirectional authentication where the module or the endpoint that has an authenticator can be paired up with the host side or the ECU to make sure that it's a genuine ECU talking to it. And then it also, the ECU, conversely, can look at data, look at signatures coming from the authenticator, and know that it's coming from a valid source. So one way to do this, Maxim has a portfolio called DeepCover Authenticators that serve this area of the security market. So I wanted to thank you for listening to my talk, and certainly if you would like to have more information about this, you can visit Maxim's website and also look for our DeepCover embedded security technology. Thank you.